Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Michael Faraday's On Lines of Force, presented as 1831, represents a pivotal moment in the development of electromagnetic theory, moving away from the action at a distance paradigm prevalent at the time towards a field-based understanding. This essay undertakes a meticulous examination of the claims made within this seminal work, assessing its internal coherence, evaluating the evidence presented, and contextualizing its significance in shaping subsequent scientific thought. We shall delve into the specific arguments and observations Faraday advances, analyzing the structure and logic of his reasoning as he lays the groundwork for the concept of lines of force. A detailed dissection of each section of Faraday's paper will reveal the gradual evolution of his conceptual framework and the experimental basis upon which it rests. Section 1: Introductory Observations. Regarding electromagnetic induction, Faraday begins his paper with a series of observations regarding the relationship between magnetism and electricity, particularly focusing on the phenomenon of electromagnetic induction. He asserts that magnetic force acting upon a conductor can induce an electrical current, a claim that deviates significantly from prevailing notions of static and distinct electrical and magnetic forces. Faraday's initial statements demonstrate a keen awareness of the limitations of existing theories in explaining experimental results he has observed. A central claim in this initial section involves the assertion that the movement of a magnet near a conductor generates electrical influence in a way that mirrors chemical reactions. This analogy, while not perfect, allows Faraday to establish preliminary ground for conceiving of electromagnetic effects, not as instantaneous actions across a distance, but rather as interactions occurring through space. Examining his experimental setup reveals that the induced current is transient, occurring only during the magnet's motion, or when the electromagnetic field is changing. This observation is crucial as it leads to the formulation of the principle that a changing magnetic field is required to produce an electric current. Faraday's initial claim hinges on a series of experiments involving coils, magnets, and galvanometers. The methodical arrangement of these experiments and the accurate recording of the resulting deflections observed on the galvanometers provide strong empirical evidence for his assertion. This initial exposition establishes the foundation for understanding the mechanisms through which magnetic forces can induce electrical currents. Section 2: Delineating the geometric properties of magnetic curves. This section addresses the geometric characteristics of magnetic curves, now known as magnetic field lines. Faraday proposes, through observation and experimentation, that magnetic force does not emanate from a magnetic pole in a single direction but rather spreads outward following specific curves. He argues that these curves, visualized by sprinkling iron filings around a magnet, represent the direction and intensity of the magnetic force. Crucially, these curves close upon themselves, indicating that the magnetic field forms closed loops. Here, Faraday postulates that these lines of force are not merely a convenient visualization but actively exert a physical influence. His claim suggests that these lines represent the medium through which magnetic force acts, implying a departure from the action at a distance viewpoint. Faraday's argument relies on the observed patterns of iron filings around magnets and on the behavior of compass needles placed within a magnetic field. He uses these observations to deduce the existence and properties of magnetic curves. A challenge arises when considering that the visualization of magnetic lines through iron filings is limited by the granularity of the iron filings themselves. The accuracy in precisely rendering the magnetic field could arguably be affected. Nevertheless, the representation provides a powerful conceptual tool for studying it. This claim concerning the geometric properties of magnetic curves is a significant contribution, marking a step towards the field theory and a departure from Newtonian physics. Section 3, exploring the distribution of magnetism in metallic and other conductors. Faraday extends his examination of magnetic phenomena, probing the distribution of magnetism in metallic and other conductors, specifically under the influence of external magnets. He posits that the presence of a magnet causes a redistribution of electricity within a conductor. The movement of magnetism, he reasons, excites electrical currents in the conductor. According to Faraday's claim, the direction of these currents is governed by the orientation of the magnetic lines of force. The current flows perpendicularly to these lines of force. He argues that this interaction is not merely a surface phenomenon but extends throughout the conductor's volume. To support his contention, Faraday conducts experiments where he places metallic conductors in proximity to magnets and induces currents. He then uses galvanometers to measure the magnitude and direction of these currents, providing evidence that magnetism indeed influences the distribution of electricity within conductors. While his experimental methods are straightforward, the implications are significant. They suggest that conductors are not passive recipients of magnetic influence but actively participate in the electromagnetic interaction. This redistribution of electricity, he argued, is crucial to the generation of induced currents. However, the exact mechanism by which magnetism manipulates charges within conductors remained somewhat unclear in his explanation. He lacked the detailed understanding of electron movement within metals, which came later with the development of quantum mechanics. Section 4, investigating the influence of magnetic fields on light. Faraday delves into the relationship between magnetic fields and light, a proposition initially met with considerable skepticism among his scientific peers. He posits that a strong magnetic field can rotate the plane of polarization of light passing through a transparent substance. This phenomenon, now known as the Faraday effect, provides a crucial link between electromagnetism and optics, laying the foundation for the later development of electromagnetic theory of light. Faraday bases his claims on meticulous experimental observations, wherein he passes polarized light through a block of heavy glass placed between the poles of a powerful electromagnet. By carefully measuring the rotation of the plane of polarization, he demonstrates that the magnetic field directly influences the behavior of light. The significance of this experiment lies in its implication that light and magnetism are not separate phenomena, but are instead interconnected aspects of a more fundamental underlying reality. While previously there was little evidence to connect the two forms of radiation, the Faraday effect offers evidence that they are linked. It is important to recognize that Faraday's observation of the rotation of light's plane of polarization was not initially explained with a comprehensive theoretical framework. The mechanism behind the interaction between light and magnetism remained mysterious until the development of Maxwell's equations and the subsequent understanding of light as an electromagnetic. Section 5, exploring the nature of dielectrics and the presence of electricity. In this section, Faraday extends his investigation to dielectrics, exploring their behavior in the presence of electric fields. He proposes that dielectrics are not merely passive insulators but actively participate in electrical interactions via a phenomenon he calls electric induction. Faraday argues that when a dielectric is placed between two charged conductors, it becomes polarized, with its constituent molecules aligning themselves along the lines of electric force. This polarization, he suggests, enhances a capacitor's ability to store charge and plays a critical role in electrostatic phenomena. Faraday supports his claims with experiments involving capacitors filled with different dielectric materials. He observes that the capacitance increases as the dielectric constant of the material increases. The increase in charge storage capacity is attributed to the polarization of the dielectric medium. He correctly infers that the dielectric medium allows more charge to be stored at a constant potential difference. Faraday's analysis of dielectrics is groundbreaking. It moves away from the conventional understanding of dielectrics as passive insulators to a view where they are integral to the electrical phenomena. This concept of polarization lays the groundwork for understanding the microscopic interactions between electric fields and matter. It is worth noting that Faraday's description relies on a somewhat simplified model of molecular polarization. A more complete treatment requires considering the specific structures and properties of individual molecules, requiring an appreciation of the quantum level. Section 6 Faraday's conception of action through contiguous particles. Faraday explicitly addresses the concept of action at a distance, a notion that contrasts with his evolving understanding of electromagnetism. He proposes that electrical and magnetic forces do not act instantaneously across empty space, but instead act through a continuous chain of contiguous particles or lines of force. This idea challenges the established Newtonian view of gravity as an instantaneous force exerted between objects, regardless of distance. Faraday argues that the intervening medium plays a crucial role in transmitting electrical and magnetic forces. The idea that an electromagnetic force propagates through a medium is a radical departure from the established physics of the time. To support his argument, Faraday draws upon observations of polarization in dielectrics and the behavior of magnetic lines of force around magnets. He suggests that these phenomena cannot be adequately explained by action at a distance. They require a recognition of the role played by the medium. Faraday's rejection of action at a distance is a cornerstone of his electromagnetic theory. He is advocating instead for a field-based understanding of how forces propagate. He recognizes that the mathematical tools available at the time restrict him from formulating a full theoretical framework. Faraday's conceptualization of force acting through contiguous particles is ultimately validated by the development of Maxwell's equations. They demonstrate that electromagnetic forces propagate as waves through space, with the electric and magnetic fields acting as the mediating medium. Section 7 Further elaboration on the properties and physical existence of lines of force. Faraday strengthens his assertions about the physical existence of lines of force, arguing that they are not mere mathematical constructs but represent real physical entities possessing specific properties. He claims that these lines of force are capable of exerting mechanical forces, such as tension along their length and repulsion perpendicular to their length. In turn, this explains the attraction between opposite charges and the repulsion between like charges. According to his claim, the lines of force create a kind of stress in the medium, which in turn causes the observable electromagnetic effects. Faraday's claims are based on his observations of the behavior of magnets and charged objects. The patterns of iron filings around magnets indicate something is physically present in the space surrounding them. The attraction and repulsion between charges and magnets support the idea that the lines of force exert a mechanical influence. Faraday's insistence on the physical reality of lines of force is crucial for the development of field theory. It provides the conceptual link between the abstract mathematical description of fields and the tangible effects of electromagnetism that can be observed. While Faraday does not provide a complete explanation of the nature of these lines of force, his assertions pave the way for future investigations into the underlying structure of the electromagnetic field. The idea that the lines of force possess both tensile and repulsive properties is a bold and potentially problematic claim given the limited theoretical framework available. Nonetheless, it proved to be immensely fruitful in guiding future researchers towards a deeper understanding of electromagnetic phenomena. Section 8. The significance of Faraday's conceptual revolution and its impact on contemporary theories. Faraday's conceptual revolution in electromagnetism greatly impacts contemporary theories. He challenges the traditional view of forces acting instantaneously across empty space. This new perspective is rooted in the belief that forces are transmitted through lines of force. According to his observations, these lines fill the space between interacting bodies. Faraday's assertion that space itself is a medium for the transmission of electromagnetic force is a departure from the prevalent scientific view. His thinking, at the time, ran counter to the dominant Newtonian paradigm. He claims that electromagnetic phenomena are best understood as interactions within a continuous field, where the lines of force serve as the pathways for this interaction. His ideas suggest a shift in perspective from particles acting at a distance to fields permeating space. Faraday's work on electromagnetic induction provides crucial experimental evidence challenging the traditional view. His experiments demonstrate the interdependence of electricity and magnetism. This discovery underpins his concept that forces are transmitted through lines of force rather than acting at a distance. The impact of Faraday's work is not immediately fully appreciated, due in part to the lack of a suitable mathematical framework to express his ideas. Faraday's concepts are ultimately formalized in Maxwell's equations. These equations provide a mathematical representation of the electromagnetic field. Maxwell's theory validates Faraday's intuition about the importance of the intervening medium in mediating electromagnetic interactions. Section 9 Examination of Faraday's experimental methodologies and their influence on results. Faraday's reliance on experimental methodologies profoundly shapes the results of his investigations. He demonstrates the significance of empiricism in science. Faraday avoids developing complex mathematical models and focuses on detailed observation and experimentation. His work highlights the value of direct observation in uncovering fundamental physical principles. His claim asserts that carefully designed experiments are essential for making reliable inferences about natural phenomena, especially when existing theories are inadequate. According to his view, experiment serves as the ultimate arbiter of scientific truth. Faraday's experimental techniques are characterized by their simplicity and ingenuity. He uses relatively simple apparatus such as magnets, wires, galvanometers, and other items to carry out his experiments. His results are derived from careful observation and analysis of the phenomena. Faraday's discovery of electromagnetic induction is a testament to his methodological approach. He methodically explores the relationship between electricity and magnetism. Faraday's experimental approach has an influence on the direction of scientific methodology. It emphasizes the importance of direct observation and experimentation in advancing scientific knowledge. His work motivates future scientists to adopt a more empirical and experimental approach in their research. Section 10 Analysis of Faraday's writing style and communication of abstract scientific concepts. Faraday's writing style directly influences the dissemination and understanding of his abstract scientific concepts. Faraday employs a clear and descriptive style. This approach allows him to effectively communicate complex ideas to a broad audience. His claim centers on the idea that effective science communication requires clear language and avoidance of jargon to make it understandable to all audiences. According to his practice, the best way to explain science is through simple and direct exposition. His descriptions of lines of force provide a clear visual representation of abstract concepts. His analogy for chemical reactions further aids in grasping the nature of electricity. Faraday's ability to make abstract concepts accessible contributes to the widespread acceptance of his ideas. By using clear prose and avoiding complex mathematical derivations, he broadens his influence. This contributes to the development of scientific thought. Faraday's commitment to clear communication aligns with his belief in the importance of disseminating scientific knowledge to all. He argues that science should be accessible to the public, not confined to a small group of specialists. His clear style is a model for future scientists. They emulate his approach to effectively communicate their findings and contribute to a wider appreciation of science. Section 11 The enduring legacy of lines of force and their influence on modern physics. The enduring legacy of lines of force continues to shape modern physics, providing a conceptual bridge between classical and modern physics. Faraday's contribution endures. He laid the groundwork for the development of field theory, which is central to our understanding of fundamental forces. His claim asserts that the concept of lines of force fundamentally altered the way scientists understand forces and fields. According to modern understanding, quantum field theory builds on Faraday's ideas, describing forces as mediated by fields. His ideas suggest that the universe is governed by interplay of interconnected fields, not instantaneous actions. Faraday's notion of lines of force evolves into the modern concept of electromagnetic fields. These fields are the basis of the standard model of particle physics, providing a framework for understanding fundamental particles and forces. Electromagnetic interactions are mediated by these fields, reinforcing Faraday's vision of interconnectedness. The influence of lines of force extends far beyond electromagnetism. He creates a foundation for understanding gravity, quantum mechanics, and other areas. His framework encourages scientists to view nature as a system where forces and fields interact. Faraday's vision of interconnectedness continues to inform modern scientific thought. In conclusion, Faraday's On Lines of Force represents a profound shift in scientific thinking. His meticulous experiments, insightful observations, and innovative conceptual framework revolutionized the understanding of electromagnetism. By challenging the action at a distance paradigm and introducing the concept of lines of force, Faraday laid the groundwork for the development of field theory, which remains a cornerstone of modern physics. While some of his claims lacked a complete theoretical underpinning at the time, his work proved remarkably prescient, guiding future generations of scientists towards a deeper understanding of the fundamental forces governing the universe. His legacy extends beyond his specific discoveries, influencing the very methodology of scientific inquiry and emphasizing the importance of experimental observation and clear communication. Faraday's intellectual audacity and dedication to empirical evidence cemented his place as one of the most influential scientists in history, and his concept of lines of force continues to resonate as a testament to the power of innovative thinking.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.